our first speaker is our review talk from Christine Chen, who's going to talk about planetary systems, formation and evolution as seen by JWST and future missions. So Christine, thanks for being here. It's all yours.
Great, thank you. Thanks for the introduction. And thank you to the organizers for the opportunity to be here today to talk to you about, well, I'm a big fan of both JWST and disks, and so I did a last-minute sort of switch on the title of my talk to the JWST disk revolution. And this, for me, is both, I think, a reflection of what I feel like I've been seeing in terms of the JWST observations that have been made in the first few cycles of JWST. And it's also a little bit aspirational in terms of thinking about the long-term impact of JWST on disk science. And my hope is that JWST will do for disk science what ALMA has done for disk science. And so this is a figure drawn from a Nature Astronomy editorial in which they were noting the increase in angular resolution afforded by ALMA and how that's really driven the field forward. And you can see now with JWST providing access to a new wavelength range is changing our picture of disks. I guess before I go too much further, I want to say also that there have been so many outstanding observations that have come out recently that it's hard to mention all of them. So I've tried to hit some highlights in terms of things that I thought were interesting, and then also to call out presentations by people here. So you'll see talks, with the red box around them and posters with the green box around them. From a sort of historical point of view, when we think about disks, we characterize them typically both in scattered light and in thermal emission. And it's the scattered light that has previously really required the high contrast performance. But JWST extends into the mid-infrared and gives us the opportunity to study thermal emission. So I'm actually going to talk about not just high contrast imaging technique data, but also other data, thermal emission data as well. And like so many of the other speakers so far today, I'm also going to talk a lot about spectroscopy, because I think this is one of the things that JWST has really enabled and is really pushing the forefront of our understanding. This is the classic picture that we're all familiar with in understanding sort of the role of disks in star and planet formation. So disks are a natural consequence of the star formation process. When you have a knot and a molecular cloud collapsing to form a star, it has a little bit of angular momentum associated with it, which then supports the formation of a disk. It can be early on still enshrouded in an envelope, and during this phase it's called a protostar. And over time the envelope accretes, and you have a disk which is rich in both gas and dust. This is a protoplanetary disk, and here we think that there are the building blocks for gas-rich planets. And then over time that gas accretes onto the star and onto planets, so that by the end you have maybe a planetary system containing planets, planetary embryos, planetesimals, and we refer to this as a debris disk. So I would say at the time of the previous LEO meeting, there had been a lot of emphasis in terms of observations on what we could learn from imaging through high contrast imaging techniques, looking at disks around both protoplanetary and debris disks. And one of the key questions that people sought to answer was, how do planets form in these disks? Planets are massive, and so they dynamically perturb the gas and dust in the disk and create structures that are signposts for planets. With JWST, what I'm tremendously excited about is now the opportunity to obtain spectra to understand what the content of the solid materials is and the gas materials. JWST particularly enables spectroscopy at 3 to 5 microns, where there are a number of ice features, the most prominent of which is water ice at 3 microns, but then other common ices as well, such as CO2 at 4.2 microns, and CO ice also at about 4.7 microns. And I would say that JBST is really revolutionizing our idea of star formation by providing access to these ice solid state features in the near infrared, but then also in the mid infrared as well. And so you see now the contribution by MIRI at wavelengths longer than 5 microns, which provides access to complementary ice features. So for example, there's an additional CO2 feature at 15 microns seen here. And so there are these beautiful observations that are showing us the trail of water through the star formation process. And this helps us to understand how water is incorporated into planetary systems. In our own solar system, we want to know how Earth accreted its water, and for context, we'd like to know whether that process is available in other planetary systems or whether or not the terrestrial planets and those systems accrete their water through other processes. In addition to solid state features, we can also study gas in these disks. The gas is very complementary to the solid state, particularly with volatile ices where you have sublimation, for example, that moves things between the solid phase and the vapor phase. And for me, as a person who's been studying disks more in the later phases of evolution, I'm really interested in understanding what the composition of these disks is and how and when the bulk gas dissipates. This is important because it sets the timescale for giant planet formation. So this is sort of an outline of what I'm hoping to talk to you about today, just as sort of presented in the introduction. So trying to understand through studying disks how planets form. So one major theme from observations within the past 20 years has really been trying to infer the presence of planets by looking at signatures imprinted on the disks. But more recently, we've also been able to see the late stages of, for example, terrestrial planet formation through collisions, so witnessing planetesimal collisions. And then these other questions now moving beyond sort of imaging observations into spectroscopy of understanding the role of water and gas as a tracer. So within the past decade or so, there have been amazing observations of disks, particularly from high contrast imaging observations using, for example, SPHERE and GPI. This happens to be a compendium of observations taken with SPHERE of protoplanetary disks that shows the wide variety of structures that have been seen in these disks, from rings to spirals, broad shadows, narrow shadows, and many of these signatures we think are indicative of the presence of planets that have not yet been detected. As an example of some of the work that people are doing from the ground today, this is a result from Bin Ren, who has been looking at snapshots of protoplanetary disks over time to try to understand how the spiral arms move over timescales of a few to 10 years. If the spiral pattern is driven by a companion, then the whole pattern should rotate with a fixed speed, whereas if it's not, then instead you should expect to see the spiral arm at different radii rotate at the Keplerian velocity. And so this is a really beautiful result that Bin showed, where he measured the spiral arm pattern speed for this particular target, V1247 Ori, and based on the motion that he saw, he could constrain where the planet was likely to be located, including its orbital period. And just laying that orbit on top of the ALMA observations, you can see that it's consistent with the gap that we see that's carved there. In addition to direct imaging, there's also been STI looking in and out of spectral features such as H-alpha accretion. And I just wanted to flash this very nice result from John Lin Lee on looking for H-alpha, or the discovery of a protoplanet that's accreting through H-alpha. And this is another theme that I think the ground continues to really excel at, and just highlighting some presentations during the meeting on these topics. So I'm going to shift a little bit to tell you about how JWST is able to provide a complementary picture on some of these questions. And so for JWST now, when we move to MIRI, we already heard a little bit of some of the spectacular thermal emission images that have been seen. We know for some planetary systems that they contain probably multiple planetesimal belts. And this is inferred from their spectral energy distributions. What happened? Oops, oh dear. Their spectral energy distributions. And so this is the case for HR 8799, where you can see the spectral energy distribution here, and there's these two components that correspond to dust interior to the 4 giant planets and dust exterior. And this is further reinforced by images that were taken with Spitzer and Herschel with very low resolution, showing the approximate sizes of these two regions. And there's some really beautiful now follow-up imaging from Anthony Boccoletti of this system showing direct imaging constraints on the location of the asteroidal dust. There's also imaging of systems that don't apparently contain very massive planets. This really beautiful image that was obtained by Andras Gaspar of Fomalhaut. And there was a very nice paper that was published last year by Max Sommer looking at mechanisms by which you could create this very extended inner disk. In the paper, Max hypothesizes that the planetesimal ring and the outer part, which is analogous to a Kuiper belt, is a source of particles that are dragged inward by the Poynting-Robertson effect. And he's able to reproduce the radial distribution of dust as seen in the observations, and to also constrain the dust properties. So we'll hear more about drag-dominated debris disks from Andras next. One of the things I think has been particularly cool has been the discovery of so many disks in surveys where the original intention was to find planets. Aaron already mentioned this, but I wanted to highlight a couple of cases that Katie Kratz is working on. There has been an outstanding mystery in debris disks about where are the debris disks around M-type stars. And it was originally hypothesized that we don't find them because the M stars have very low luminosity, and so they're not able to heat up their circumstellar dust, and you don't see any far infrared excess, for example. And that seems really to be borne out by some of these discoveries that are being made, in which there's a disk that's clearly seen in scattered light, but when you look at the spectral energy distribution, there is not a clear or strong signature for infrared excess. Another flavor of work that people have been doing from the ground has been to constrain the properties of the dust in debris disks, for example, by measuring the scattering phase functions. So this is how the intensity of the light changes as you go around the ring, because you're changing how much the light is deflected between the star, the dust, and you, how much it's changing from forward scattering. So in this particular work by Justin Holm, you can see that debris disks so far seem to have very similar scattering phase functions. They're very forward scattering, sort of similar to the dust that's seen in Saturn's rings. And so there is work ongoing. Andras, again, is going to talk about NIRCam observations, and Briley Lewis is going to tell us about, has a poster about revisiting ground-based observations. I think other dynamical things that we've learned from imaging have been, for example, the activity of collisions in debris disks. I think the most spectacular of which has been the direct images of Fomalhaut. And so there was a paper, that originally Paul discovered a point source in Fomalhaut, which was later described as an expanding dust cloud by Andras. And I don't want to steal Paul's thunder, but I know he's going to tell us about a new point source or possible dust cloud that he's found. But these discoveries of active collisions aren't limited to HST observations. We find evidence for them in the JWST data as well. And so as an example, here is the cat's tail, and this really interesting structure that's been discovered, and which has been modeled, assuming that there's been a giant collision at about 85 AU away from the star, and then radiation pressure is blown dust out into a stream. And then, as was mentioned earlier, this change in what the mid-infrared spectrum looks like from a very strong solid state feature-rich spectrum to one in which the features are gone, indicating the dust has been blown out of the system. So I think Katie is going to tell us more about modeling the disk structure of beta PIC here. So that was a whirlwind tour kind of the flavor of science that I think people have been doing and that JBST is building on from ground-based observations, for example. And so I'm going to try and move into some of the things that right now I feel like are somewhat distinctive for JWST. So one of the key science questions that I think we have is, how did the Earth accrete its oceans? And by extension, you know, are other exo-Earths rich in water? And if they are, how did they accrete their oceans? Did they accrete them through the same pathways as the Earth, or are there other pathways by which they acquired their water? And when we study our solar system, one of the key constraints that people use is the deuterium fraction of mean ocean seawater, which is shown here as the blue dashed line across this plot. And because the water on Earth is thought to be inherited from other places in the solar system because the Earth formed dry, people have looked at the deuterium ratios in other objects in the solar system to try to tease out what's the origin of Earth's water. And supporting the NEISS model, it appears that carbonaceous meteorites, so material from the outer asteroid belt, have very similar compositions or deuterium ratios, and so that's become the leading explanation for the origin of Earth's water. But when we think about disks, disks modify their circumstellar environments because the central star is warm and it's luminous and it heats up its environment. And so this sets up different sublimation fronts within the disk. So for the most volatile species, these only exist in the outer disk. And then as you move closer and closer to the star, you begin to lose the more and more volatile species until in the more inner parts of the disk, you just have water and then finally no ice at all. And so we can learn something about how the solids contribute to planet formation by studying the ices in these particular regions. So the JBST observations have been absolutely tremendous for studying ices in disks. These are observations that were obtained by Ilaria Pascucci for 4 protoplanetary disks using the NERSPEC IFU. And you can immediately see that there's these very prominent 3-micron water ice features. They all indicate amorphous water ice. There's also CO2 ice and CO ice as well. And around the CO ice, you might see there's a little bit of fuzz here. This is indicative of rho vibrational emission of CO. So this is a CO that has a delta V, a change in the vibrational quantum number of about 1. So in this particular case, the spectra have been extracted from the scattered light sort of nebulae above and below the midplane of the disk, and you can see in reflected light these water ice and other ice signatures. But what if you want to study the content of the optically thick part of the disk? There have been some really intriguing studies looking at trying to understand whether you can infer the composition of the midplane material by looking at the distance between the 2 nebulae, scattered light nebulae on either side of the dark lane. And so these are also NERSPEC IFU spectra, but now measuring this distance between the 2 nebulae as a function of wavelength. And you can see that it finds peaks at 3 microns, 4.2 microns, 4.6 microns that are coincident with volatile ice features, indicating that indeed, because the opacity increases due to the presence of ices, you can infer the presence of ice by looking at this thickness of the disk. But unfortunately, we can't study all disks with the IFU. The previous examples that I showed you lent themselves well because they were edge-on disks, and so the disk is optically thick and it occults the star. But there are cases in which this is not true. And in these particular cases, we can try to apply high contrast imaging techniques using NIRCam, particularly in the 3 and 3.6 micron filters, to try to understand whether or not there's water ice in these disks. And so this is a result from a paper recently published by Max Miller-Blanchard for the ERS target HD 141569 observed with NIRCam. And you can see this is the NIRCam image in the middle. This is a visual scattered light image on the left. It's HST STS. And on the right, what Max is showing here is the ratio of the 3 micron to 3.6 micron flux. So if there's more water ice, it means there's a deeper feature, so there's less 3 micron light compared to 3.6 micron light. And so one of the things that you notice in this plot is that this is an opportunity to search for stellocentric gradients in the composition of ice, in the ice properties in these disks. And that for this particular one, something seems like it happens at about 200 AU, because interior to that distance, there seems to be either more water ice because there's a deeper feature, or there's some sort of change in the minimum grain size, and compared to the outer part of the disk where this ratio is less. This kind of behavior is something that we already see in our solar system. There have been beautiful surveys of the spectra of TNOs in our solar system, and they have found essentially that most TNOs fall into 3 categories. Either up here, the blue spectrum, these are called bowl spectra, and they're dominated by water ice. The middle one in yellow is it's called a double dip spectrum, and it shows strong CO2 features. And at the bottom, in red, this is a cliff type spectrum, again from 1 to 5 microns. You can see in the middle here that a lot of them have this sort of very strong OH stretch, which is due to water, but can be due to hydrated materials as well. The explanation that's arisen for why there are these different classes of KBOs is that essentially the composition is a key to telling us where the KBOs formed. And so since water is the most durable of the volatile ices, these water ice KBOs are likely the ones that formed closest to the sun, followed by these CO2-rich ones, and then the ones that are rich in complex organics. So in cycle 1, I was really excited to have the opportunity to study 3 debris disks using NIRSpec IFU, and this is work that has been led by Chen. These are observations of a debris disk called HD 181327, and you can see here on the right side, this is a slice of the NIRSpec IFU data cube. It looks deceptively small here. This is actually a 3x3 mosaic, so it's 9 arcseconds on a side. In this particular case, the disk in reflected light is pretty faint compared to the host star, and so we had to apply reference PSF subtraction techniques to reveal the disk. And even in doing so, there's still regions of the data that are heavily saturated, so it's hard to study them. But Chen has done a beautiful job extracting the spectra from these observations and showing that there's actually a gradient in the composition of the dust radially. The innermost region from which he extracted data doesn't really show a strong water ice feature. It's just a continuum. But as you move to the outer part of the disk, you start to see this 3-micron water ice feature. And then what's even more striking is you see a Fresnel peak at 3.1 microns. The Fresnel peak is important because it tells us that the water ice in this disk is crystalline and the grains are large, which was unexpected, particularly just the overall similarity with the appearance of Kuiper belt spectra. And then as you move to the outer part of the disk, you see it becomes even icier. So Chen compared the spectra of HD 181327 with different TNO classes. So these are, again, the water-rich, CO2-rich, organic-rich. And then these centaurs are essentially H2O-rich KBOs, but they're closer to the sun. And so they've been more heavily modified by radiation. And you can see they're actually a pretty good match for the spectrum of the debris disk. So in the program, there was not only HD 181327, but there was also a beta pic as well. And so these are the observations of beta pic that were obtained and that Sarah Betty analyzed. And so on the left-hand side here, you can see this is now a slice of the NIRSpec IFU data. And then you can see spectra that have been extracted from either side of the disk. So this is really fascinating because when you look at this spectrum, it looks quite a bit different qualitatively compared to the 181327 spectrum at 1 to 5 microns. They both contain 3-micron water ice features, but the shape of the water ice features is very different between the two targets. This particular one does not show the Fresnel peak, and instead it has a pointier trough to the feature, which is peaked at 2.9 microns. This is consistent with the water ice being amorphous rather than crystalline. So it's really remarkable to me in this study where we have 2 detections of water ice around stars that have the same age, because they're both in the beta pic moving group, and they have very similar luminosities. 181327 is an F6 star, this is an A5 star, that you have such different water ice properties. So this begs the question of why is the water ice in 181327 crystalline and why is the water ice here amorphous? Well, one possibility is that when the ice was condensed and formed in the disk, was incorporated into planetesimals, it was incorporated as amorphous ice. This is what is thought to have happened in the solar system, and solar system workers have long looked for amorphous ice in our solar system and been unable to find it. And so we don't know if that's one possibility. Another is that there could be cycling of the water from the solid phase to the vapor phase, so that as the parent bodies come close into the star, they sublimate, release vapor, which moves out to the outer parts of the disk and recondenses as amorphous material. So those are possibilities for why this disk could have amorphous water ice. In 181327, we don't know about the processing. One possibility is that this disk is stirred by unseen planets, and that creates the relative velocity within the planetesimals to be relatively high, so that when they collide with enough velocity that they actually change the phase of the ice from amorphous to crystalline. So I think that's a really interesting, outstanding question. The beta pic ice spectrum here is similar to 181327, or different from 181327, in that there's the detection of CO2 ice, and you can see some fluorescent CO gas here as well. And Sarah did a really wonderful job really zeroing in on the 13th CO2 feature to try to understand in detail what the composition of the ice is. And so you can see the spectrum here shown as a black histogram compared with laboratory data. And this is a similar kind of plot, except for now you have the full width half maximum as a function of peak position. And what she's shown is essentially the data are best reproduced by this sort of orange line here. which indicates that this is not pure CO2 ice. It's actually CO2 ice that's a minor constituent within water ice at the about 10% level, which is consistent with what's seen in comets. So we feel that these observations really hang together because our expectation is that the amorphous water ice should be cold to remain amorphous, and the spectrum tells us, based on the full width half maximum and peak position, that the ice is cold. So the last thing I'd like to talk about for a little bit is volatile gas in disks. I think that this has been a really exciting growth area in disks. This is an example of a Titari spectrum obtained with MIRI. And you can see that there's this absolute forest of water emission lines. And you can see other minor constituents such as CO, CO2, et cetera. This was originally discovered with Spitzer, but is being studied in exquisite detail now with JBST MIRI. There are now spectra of maybe 300 of these objects that have been taken, and there have been some very nice studies comparing what the spectra look like depending on the ALMA geometries for the disk. So I point you to this one particularly interesting study by Andrea Bonzatti that showed that the compact disks actually have an excess of cool water at 170 to 400 K, which is indicating that perhaps the reason why they have this extra cool water is that there is icy planetesimals that are crossing the sublimation boundary, the water ice sublimation front, and releasing water here. But the observations have shown us not only these fantastic spectra for Titari stars, but some really intriguing results for lower mass objects as well. These very low mass stars and brown dwarfs that have masses less than 0.2 solar masses. In contrast to Titari stars, the spectra of these objects are not oxygen rich, they're carbon rich. And typically the largest feature that's seen here is acetylene as C2H2. And there's an autocorrelation that has been seen between the flux ratios of acetylene and water and the luminosity. So the higher luminosity Titari stars are more water rich, whereas the lower luminosity, very low mass stars are more acetylene rich. And there have been some really intriguing sort of parallels between the spectra of these disks around very low mass stars and those of companions in disks. And there are a couple of results here at the meeting talking about this, I think, that are really interesting. But volatile gas has been seen not only in protoplanetary disks, but it's also been seen in debris disks as well. This is a beautiful result from Kate Su using the MIRI MRS. When you look at the spectrum, the first thing that your eye is drawn to is this very prominent silica feature at 9 microns. It's a solid state feature. But if you look carefully at the continuum down here and you blow it up, you can actually see that there is emission from CO2 at the few sigma level. This is a really exciting discovery because it appears that the CO2 is cospatial with the silica that's seen at 9 microns. So this is likely created by gas and dust in the very inner region of the disk. So there was probably a giant impact or some sort of atmospheric stripping event that destroyed carbonaceous chondrite-like parent bodies. But it turns out for debris disks, there are not only volatile gases, molecular gases, but also atomic gases seen as well. This is a beautiful result from Matthias Samland from the MIRI MRS GTO team, looking at the star HD 172555, which is another giant collision target. It also has a very silicate-rich, or silica and silicate-rich 10 micron feature. But what was really surprising about this was the detection of volatile and refractory atomic gas lines. So sulfur 1, chlorine 1, nickel 2, iron 2. And you can see the insets here from the spectra. And it was remarkable to me that when Matthias saw this data, he actually could see that the lines are rotationally broadened due to Keplerian motion. To me, this is extraordinary because the data is just an R3000, so the gas has to be moving very, very fast for this to happen. So indeed, he estimates the gas comes from the inner 0.3 AU, and so may be generated by the sublimation of rocky materials deep inside the terrestrial planet zone. This is in contrast to other volatile and refractory gas seen in beta Pic, which has a different abundance pattern. These are observations from my GTO Cycle 1 program that were analyzed by a JHU graduate student, Caden Worthen. And in this particular case, Caden has done STScI, differencing within the argon line and the continuum to reveal this argon-2 emission, which is coincident with the disk as seen in thermal emission. There is a beautiful follow-on study from Yanqing Wu trying to understand what the line emission means for the underlying abundance of the different atomic species. And in this work, Yanqing showed that this particular disk is enhanced in volatile species, so carbon, nitrogen, oxygen, argon. And so the hypothesis is that this gas is instead created by the destruction of icy planetesimals in the outer part of the disk. But in addition to these wonderful observations, JBST has been shedding new light on carbon monoxide gas. So carbon monoxide we traditionally think of as being studied with ALMA in the pure rotational lines. But indeed, JBST provides access to row vibrational lines instead, particularly the fundamental, where the change in the vibrational quantum number is 1. And when these observations were made in cycle 1, it was actually a little bit surprising. It wasn't expected. So there was a paper that was recently published, a beautiful paper by Cicero Liu, on observations of a SCO-SEN disk, HD 131488, in which you can see a snippet of the spectrum here from 4.5 to 5.1 microns. And you can see this forest of CO emission lines here. What's remarkable is that this gas is not excited, through LTE. It's actually fluoresced instead. So there's UV pumping by the star of the gas, which excites it. The thing I think that's really interesting about this CO fluorescent emission is that it has the potential to be a much finer tracer of gas and disks than the ALMA CO observations. So this is a nice plot that Cicero made showing a CO mass as a function of distance, and then all these blue dots that you see here are disks that have been detected by ALMA, including HD 131488. And then you can see for a comparison the mass of gas that's detected in fluorescence. It's fully 6 orders of magnitude less than the ALMA mass. And so you can imagine that there are situations in which you may not see any ALMA emission, but you could see fluorescent emission. The fluorescent emission has also been, in this particular case now, imaged in 49 SETI. This happens to be low resolution data rather than the higher R3000 data that Cicero was looking at. So this is NIRSpec IFU data. This is an image where there's a difference between the the image in the CO line and then just adjacent to it so that you can see where the emission arises from. And then these are the extracted spectra. Since the spectral resolution is so low, you have lines being blended together into bands. And so you can see, for example, the 1 to 0 band, the 2 to 1 band, the 3 to 2 band, and so on. When this data were originally taken, I was sort of skeptical about how much we were going to be able to really learn from these observations, but Caden's done a really wonderful job of interpreting it. And he's shown that essentially you need 2 different components of gas in order to reproduce the observations. One that's quite hot, so it has a temperature of 5,300 Kelvin and a rotational temperature of 41 Kelvin. So this is the fluorescent gas that's UV pumped by the star. But there is also this component that you see here in blue. This is a warm component with a vibrational temperature of 600 Kelvin, which is more consistent with IR pumping. So the picture you should have in your head of the disk is that these infrared lines give us an opportunity to do CO tomography when combined with ALMA observations. And so this is an edge-on view of the disk showing the different emitting regions. So the UV fluorescent emission comes really from the surface. The IR pumped emission, because the IR photons penetrate more deeply, comes from sort of like the interior, and then the ALMA CO is from the midplane. And so by measuring the temperatures of the gas, we can try to understand what the H2 to CO ratio is, for example. So I'm just going to close by saying that the JWST observations have been absolutely amazing. And I'm really looking forward to the launch of the Roman telescope later this year, and in particular, the Roman chronographic instrument. And I know that we have a session on Wednesday in which we're going to hear all about Roman and the program that's been put together by the Time Prioritization Committee. So I'm super excited to hear about that. But I just wanted to remind us that this is a topic that we expect Roman CGI to contribute to. These are simulations that were made for a program led by Carl Stapelfeld, looking at the interaction of a planet with the debris disk. This particular case is HD 10647. This is a 1.4 giga-year-old star that's very close by, and it's known to have an eccentric RV planet at 2 AU. So the planet's orbit is going to be within the inner working angle of the coronagraph, but the inner edge of the disk may be just interior. And so it might be possible to see sculpting of the inner edge of the disk by the planet. So with that, I'm going to leave up my conclusions and take questions.
Okay, thank you, Christine. What questions do we have in the audience?
That is a lot, I know.
Hey, Christine. Christine, thank you so much. That was a very fantastic and comprehensive review. So I guess mine is more of a comment. You showed this result for 181327 where the composition appeared to change dramatically going from the inner edge to the outer edge of the belt. And then you compared that later to some results for beta pic.
Yes.
And the results for beta pic were measured in a different region, even farther out, right? So we need to keep in mind that when we compare one disk to another, where in the disk you're making these measurements is really critical. And there's this fantastic paper by Philippe Thibault in 2014 that is undercited, in my opinion, where he shows that right at the outer edge of a debris disk, there is a beta inversion. In other words, you're actually not dominated by the smallest grains anymore, you're dominated by the largest grains. And so that it's really exciting to see that maybe we're seeing signs of that in 181327.
Okay, next question. Do you have anything more at this time? Well, I'm going to ask a question if that's okay. So you showed a lot of ice absorption features at 3 microns for a lot of individual sources. So what kind of evolution in that feature should we expect, from protoplanetary to debris disks, and when you look at a star of one spectral type versus another? Is there any framework for this?
So those are really excellent questions. And I have to say at this point, I think the answers to them are really not known. Part of the problem is that we don't have very much data, and I think the modeling is kind of all over the place. So there have been, for example, there's been work that suggests that the detection of water ice should be independent of stellar spectral type. We find anecdotally so far that that's in fact not true, and that there's an anti-correlation between stellar luminosity and the depth of the water ice feature. So for example, the 49 SETI data were originally taken to look for water ice in that disk, but none was found, and that's an A1 star. And then by the time you get to beta pic, which is like an A5 star, it's like a 10% feature. And by the time you get to 181327, it's like a 30% feature. So there are broad trends that we don't understand, and we don't understand, again, the processing of the ice in the disk. So one of the arguments for like how Kuiper belt water ice got to be crystalline is that it started off as amorphous, and that because of the migration of the planets in our own solar system, it sort of stirred the planetesimals around more so that they collided with larger relative velocities. And these like higher velocity collisions, they actually transform the ice from amorphous to crystalline. And so I think that's an interesting question is, could something like the phase of the ice be like some sort of signpost for the dynamics that's ongoing in the disk?
So does there just need to be a really large survey of a whole bunch of different axes of stellar properties to find out what's going on? Or?
So unfortunately, this is really hard work to do because you have two problems. One is that the central star is really bright, and so it saturates NIRSpec. And then the other problem is that the disk is very faint. And so essentially, unfortunately, I think within its lifetime, JWST will only really be able to study about a dozen debris disks using these spectroscopic techniques. So you can imagine expanding the survey to larger like a larger set of targets by now looking at NIRCam data and doing filter work similar to what Max did. And I think that's particularly exciting too because the bright sources that you would do spectroscopic work tend to be edge-on, whether the more extended fainter set would be more face-on and allow you to probe as a function of stereocentric radius, for example.
Okay, thanks. Do we have time for another question? Is there anybody out there? Yes.
There's a question online. So Ben Zuckerman asks, are you aware of the model that describes that Earth's water was mostly due to chemical reactions between an early massive hydrogen atmosphere and magma ocean? That is, accretion of water-rich objects may not have been the primary source of Earth's water.
I think that's an excellent point, is that, I think while understanding the origin of Earth's water serves as kind of an inspiration, I think the broader question that we're trying to ask is, where is water generically in planetary systems, and how does it move through the planetary system, from its formation and through its evolution? And is the, history of water processing in our solar system similar to or different from what's seen in exoplanetary systems?
Okay, thank you again, Christine.